In September, the Technology Policy Institute hosted an event on artificial intelligence and machine learning. We invited some of the leading experts in the field to discuss their work and the implications, opportunities, and challenges related to AI. We start by addressing the question, what is artificial intelligence?
We as scientists haven't been doing a good job of explaining to the public what AI is.
That was Kevin Leighton Brown, professor of computer science at the University of British Columbia, acknowledging that the public, the media, and researchers often all mean something different when they use the phrase artificial intelligence. We casually use it to describe technologies that can drive a car, win board games, or, some worry, to enslave humanity. In reality, AI includes a vast field of research focusing on practical applications.
AI is not an event that someday maybe will happen. AI is a portfolio of technologies that are getting evolved over time, that are with us already today, and that are continually becoming better. And whether or not 50 years from now AI builds a boy who can truly love, before that will have created a computer vision system that can look at your retina and decide if you need medical treatment.
If we think of AI as a technology that allows machines to make smart decisions, then machine learning is the process by which computers analyze massive amounts of data in real time, make decisions based on the outcome of constrained maximization algorithms, and revise the algorithms themselves as the data analysis suggests. As Susan Athey, economics and technology professor at the Stanford University Graduate School of Business, explains.
The only thing that really machine learning is doing is it's just finding sort of more, it's exploiting new computing power and some very cleverly designed and iteratively developed algorithms to do a better job sort of systematically exploring data on a large scale, especially in environments where you have lots of data and you don't really have a theory to help organize it, but you're sort of with the data help you figure it out.
As new information arrives, the machine learning algorithm will adapt to fit it.
And if the world changes, well, if I'm Amazon or if I'm Google, well, I'll just re-estimate my model. Like they retrain their model with fresh data every day or every week. So it doesn't really matter if I've uncovered something structural about cats or dogs. If people start putting cats and pianos together this week and that's the fad, I'm going to learn that pianos predict cats, even though it's in the broader world, pianos don't predict cats.
But even though machines identify these correlations and make decisions in real time, humans build in the starting assumptions and decision rules determining how the algorithms learn.
There's something in the machine learning literature called the no free lunch theorem that says you can't learn without bias. You can't learn without making assumptions. So it's kind of false to say that you can come to a learning problem given only data and figure something out about that data. It's really necessary to come kind of with data and a hypothesis, and by being guided by that hypothesis, extrapolate from the data you've got to data that you haven't seen. A big part of what machine learning researchers think about is how to be smart about making those hypotheses and how to make those hypotheses as kind of general and leverageable as possible. But I think in all science, there's a role for intuition. You need to have an idea that you want to pursue before you go off and conduct experiments and test that idea. So I think we're far from the point where machines can do science for us.
The recent advancements in AI are the result of experiencing Moore's law and compound growth over several decades.
The story of AI in the past few years has really been driven by this larger story of Moore's law causing a explosion in what we can do with computers in just the last little while. As I'm sure all of you are aware, Moore's law means that we can pack more and more semiconductors on a chip. There's been this exponential growth over time.
That computing power makes it possible to analyze the vast amounts of data we generate and also save due to large decreases in data storage costs. As Tim Huang, Public Policy and Government Relations Counsel at Google, explains, these advances have made it possible to put into practice the theoretical concepts developed decades ago that underpin AI.
Right, a lot of the kind of mathematics and a lot of the sort of theory behind it was worked out in the 80s and 90s and is really interesting as having sort of new life because of both the kind of information we can work with now and the processing power that we have access to. So one big question, and it's worth kind of clarifying, is why is machine learning different from what's happened in the past? And the way we kind of frame it up is that sort of the old way of doing software was very much based on kind of writing rules, right? So if you wanted to write a spam filter, you would say, you'd basically chain together lots of if this, then that's, right? So the engineer would say, okay, what's a pattern that we think reflects the kind of email that's going to be spam? And then I'll write rules to tell the computer to try to pick up on that. And how machine learning is slightly different and changes, I guess, some of our engineering processes is that you basically take a bunch of examples and you say, computer, take a look at a bunch of these examples, produce rules from them, and then as you see more examples, change yourself and optimize to reduce the errors.
Also, contrary to what many believe, it's not just machines improving themselves.
The real story of the actual innovation happening in Silicon Valley is massive decentralized iterative innovation where thousands of engineers are empowered to change the code that you see on Facebook, on Google, every place else, every day. An intern, if you send your kid to get a summer internship at Facebook, they can release code to the users that gets shipped to all users within a week.
The end result?
In industry, machine learning algorithms are constantly improved. So it's not like somebody had this insight, PageRank, and Google was born, and then it was static. Like Google circa 2000 is terrible today. Google 2 years ago would get trumped by today.
Continuous incremental improvements are a key part of what makes machine learning useful. But, as Chris Hammond, chief scientist and co-founder of Narrative Science, and professor of computer science at Northwestern University explains, what makes it especially powerful is that humans can't possibly match AI's ability to analyze and interpret data.
It turns out that people are phenomenally bad at data analytics, at understanding what data mean. But it turns out that it's also the case that the entire world of big data and data analytics, the world of the data scientist, is predicated on the notion that the analysis that we do of that data has meaning.
Chris Hammond's point is that humans are not generally good at synthesizing large amounts of data, which means that it's hard for us to derive actionable information from it. One objective of big data analytics and data science is to do precisely that and present it to us in a way that helps us make informed decisions. One implication is that we may not completely understand how the data pointed an algorithm to a particular conclusion. On the one hand, maybe that doesn't matter.
And my machine is a black box. I don't need to understand how it works. It's going to exploit every little detailed, spurious correlation in the data, and it doesn't really matter if that's interpretable, because all that matters is I get the right answer at the end.
But on the other hand, that raises another question. If we can't follow along, how do we know we can trust the answer? Chris Hammond explains.
It's very rare that you task an employee or a collaborator with a problem where you already know the answer and you're just messing with them. And so having it be that you go to a doctor and you say, here are a set of symptoms, and Watson comes back and says, you have thyroid cancer. And you go, well, why do you know that, Watson? And Watson says, 87%. And you're like, what? And it turns out that Watson has looked at hundreds of thousands of documents and looked at your symptoms and and found patterns matching everywhere and pulled everything together, aggregated, and gave you that score. But if it can't explain to you what that reasoning looked like or why it believes what it believes, then you have something you cannot trust.
But fully explaining its analysis is likely to be extremely difficult, especially if the algorithms change. After all, this technology is useful because it can incorporate data in ways we can't. Susan Athey digs into this set of problems in order to think about how we might open the black box in a meaningful way.
And so in some cases, people want transparency, but it's not that they need to understand how it worked. They want to understand the process of how you got there, the process of how it's tested, and they would like to see you document if there are any, like what are the racial disparities of this? What are the, who's helped and who's hurt? And if you can show people, the output and the process and how you tested it, they may be happy with it.
The reason we care about these issues, of course, is that AI has the potential to do a lot of good.
So we're going to see this massive change, and then the question is what happens to people. Now, if the cost of goods, the cost of transportation, the cost of healthcare, the cost of land go down in proportion to wages, then maybe these people aren't so unhappy because they can have a self-driving car commute them from what is a current 2-hour commute in 30 minutes into the city, and drones will deliver all their cheap goods in 1 hour from Amazon, and they're made by robots, and so they don't cost anything, and so life is good for these folks.
But, Athey continues, those positive outcomes aren't guaranteed and could also come with other problems that we'll have to deal with.
If we have a lot of concentration, there's no guarantee that just because the goods are cheap to produce, they'll be inexpensive to buy. And so if the prices don't fall in proportion to the labor costs, we're going to have problems. And I would say that even if the prices do fall in proportion to the labor costs, we still may have problems if there's lots of unemployment and lots of transition costs, and especially if the government screws up the transition.
Those are real issues policymakers should be thinking about. We don't want to lose the real benefits that AI can bring, but we also want to make sure not to leave groups behind. An important factor to consider is how human behavior will change in response. Colin Allen, Provost Professor of Cognitive Science and History and Philosophy of Science and Medicine at Indiana University, illustrates.
If I know that these cars are programmed not to hit me, does that increase my likelihood of jaywalking? Well, sure, right? I'm in a hurry, the car's going to stop, it's programmed to. So what's going to happen there? Do we make the cars raise their probability of hitting pedestrians to dissuade jaywalking? Or do we constrain pedestrian behavior in a way that now we can only cross at designated points with specific light control, so we don't let people just wander out into the road, knowing full well that the cars will stop for them? And it's this kind of feedback, I think, which makes us raise questions about what do we really want? It's not the super intelligent car that I'm having a conversation with, it's how does it affect my ordinary day-to-day experience?
That is, we can't just design AI in a vacuum. We have to take into account issues like moral hazard, where you just might decide to walk into the street if you know cars will stop rather than run you over, potentially eliminating the traffic benefits that might otherwise come from connected cars. We'll also have to answer hard questions like, whose life is worth more in different situations? Should a car always protect its driver, even at the expense of, say, a pedestrian? Susan Athey sums things up.
I think that machine learning and artificial intelligence bring great benefits in terms of efficient resource utilization, savings for government, fair treatment of citizens, where we can actually monitor the decision-making process and understand what goes into it and what comes out of it, instead of relying on human judgment, which is sometimes wrong. We can measure policy effectiveness, we can have personalization, we can have speed, we can have relevant information. But we also have a lot of risks. The benefits of this technology are unequally distributed. There's going to be a lot of displacement, lots of transition costs. The cost of living may not fall as fast as the cost of production. We may have a few people get very, very wealthy, and they're certainly not going to spend all their money, and so that money won't flow back into the economy and create additional jobs and services the way that some previous industrial revolutions did. And so if we're worried about all of this displacement, and if we see the disruption to the political process and the effective functioning of government that comes when people are unhappy, I would just say that, we should probably get ahead of this curve, because the policy solutions are actually hard, and we need to figure them out. And if we walk into these types of situations with a bad fiscal situation and a not very functional government, it's going to be very hard to manage the very difficult issues that arise through the process of this transition. Thanks very much.
Thanks for watching. For a more complete treatment of the issue, watch Professor Athey's entire talk, as well as the 2 panel discussions, which we link to below.